So we've looked at a bunch of examples where we have complementary probabilities, but it's not necessary to have complementary events to create a contingency table. As long as our contingency table includes all possible outcomes, we can use it to find probabilities and conditional probabilities. For example, suppose we have patients divided into 3 categories where 70% are in A, 10% are in B, and 20% are in C. And patients in the different categories have different probabilities of defaulting on their hospital bill. So suppose a patient defaults on their hospital bill, what's the probability they were in category C? So the probability we're looking for is conditioned on whether a person defaults on their hospital bill. So let's make D, that a patient defaults, and D complement are row labels, and whether the patients are in A, B, or C are column labels. We're given percentages to whole numbers, but our probabilities are given to 3 decimal places, so it will be convenient to work with a sample size of 100 times 1,000, 100,000. So suppose we examine 100,000 patients. Now, we know the percentages in each of the 3 categories, so we can fill out those totals. The probability category A patient's default is 0.01, so that gives us an expected number to default, with the remaining patients not defaulting. Likewise, for the category B patients having a probability of default of 0.009, and so we have an expected number to default, with the rest not defaulting. And finally, for the category C patients, we have the probability of default, so we can expect a certain number to default, with the rest not defaulting. And we can extend our totals to the number of patients who defaulted and the number who did not. Now, the patient who defaulted was one of the 930 who did, and of this group, 140 were of category C. And so that gives us the probability that a patient was category C given that they defaulted, 140 out of 930, which we can approximate as a decimal. Or we could consider one more case. Suppose 70% of a study's participants were heavy smokers, 10% light, and 20% were non-smokers. If light smokers were 2 times as likely to die as non-smokers, but only 1/5 as likely to die as heavy smokers, what was the probability that a participant who died was a heavy smoker? So the probability of interest is conditioned on whether the participant died, so we'll let a participant dying or not be our row labels, and whether a participant is a non-smoker, light, or heavy smoker, we'll let those be our column labels. Now, again, let's imagine that our study had 10,000 participants, and we know the distribution into non-smokers, light smokers, and heavy smokers, so we know the totals in each of those 3 columns. Now, we're given the relative probabilities of a person dying given their smoking status. So suppose the probability that a person died given that they were a non-smoker is some value p. So of the 2,000 non-smokers, 2,000 p died during the study. Since the probability of a light smoker dying was twice as great, then the probability of D given L must have been 2p. And again, of the 1,000 light smokers, it follows that 2,000 p died during the study. And finally, since the probability of a light smoker dying, 2p, was 1/5 the probability of a heavy smoker dying, then that probability must be 10p, and so 70,000 p of the heavy smokers died. And we can extend our total of the death row. And so we see that of the 74,000 p patients who died, 70,000 p of them were heavy smokers, and so the probability someone was a heavy smoker given that they died during the study is